My name is Pedro. I want to show you some data that was collected together with Aaron Johnson at William Dunn School of Pathology, and also done in collaboration with my colleague Louise Hughes. We've talked about difficult samples, and I want to go a little bit into how difficult can be specimen prep and how EDS can actually help you shed some light on what is happening during the specimen prep procedures. So fortunately, there was already some introduction on volume EM. I don't want to go into much detail here, but there are many different workflows that many different workflows that we must prepare our samples for. The preparation will depend on the workflow we're going for. It can also depend on the sample. So there's a lot of variables that we need to account for, especially on the preparation side, and this can be actually a lot of information for new electron microscopists starting into the field. What we want to achieve with our volumes is some contrast, and here you can see quickly segmented chloroplast of Arabidopsis, and it's being rendered on a mirror. So contrast is key if we want to analyze our structures, if we want to get our segmentation, and if we want to go towards quantitative EM. So here is where EDS can actually help you. So in EDS, your detector is collecting your characteristics X-rays that are formed when your specimen beam interacts with your sample. And the energy of the X-ray is going to be measured, and it's going to relate to the element of origin. So when you do that, you can generate your spectrum. For example, here you have the graph where you can see the energy of your elements along the x-axis, and you can see their intensity along the y-axis. So if you do this along your sample and you collect a lot of pixels, you'll be able to come up with the image you see now on the right side, where you see a lot of colors that represent the different elements of your specimen, and we call them usually element maps. So the advantage here is that we want to complement that ultrastructural data that we have with chemical composition and localization on our samples. So this should be ideal to study how the contrast is being achieved with the different stains when we do our specimen prep. For the start of our study, we decided to use some common EM stains. I also am not going to go into too much detail here. I'm happy if you contact me later to discuss that a little bit, but just so you have an overview, we've got a kind of standard EM prep. Then we went for some different volume EM preps: Starborg, Megametal, and Bropa. And they all have some variations in the amount of stains and also in the type of stains used, but most importantly, on the concentration of the stains used. So if we prepare the same sample with all the different methods, we can see by TEM that we have different types of staining with different types of staining methods that make sense. If we look at them by SEM here in the bottom, we can see that different preparations can even highlight different compartments. So we see that the Megametal has very strong membranes. We see that Starborg maybe looks a bit fuzzy. We don't have too much definition, even though there's a big contrast between the samples and the background. And Bropa seems to be somewhere in between, where you can see and appreciate some high-resolution details on the membranes, and you have some types of organelles that are more contrasted than the rest. So what does it look like when we want to compare between these staining methods in a more quantitative manner? If we look here at this plot, we try to plot here the weight percentage of different elements on the samples. We average over whole cells, and we try to measure the weight percentage of osmium, of uranyl, and of lead. The first thing we can see is that in blue the UA in blue the osmium appears to correlate with the amount of osmium that was actually put in the sample initially. So high concentration of osmium gives you a high weight percentage of osmium in the final sample. In contrast, UA seems to not correlate at all with the concentration applied during the prep, and there might even be a negative correlation here because, for example, in the mega metal, where we have 2% UA, we find a very low weight percentage of UA in the final sample. So this is kind of puzzling because what's happening with different samples, and if the concentration being used doesn't really correlate directly with the contrast that we get in the sample, there seems to be still ways to kind of optimize these protocols. Looking a little bit further into the UA concentration, we decided that, okay, we exclude the osmium. It seems to make sense. Let's look at UA on its own. And we tried to analyze 2 cell lines, RPE and HEK cells, using 3 different concentrations of UA on a free subsample. We conducted the EDS analysis, and we tried to compare different compartments in the cell. So we tried to get 10 cells per condition, and then try to see if this starts to make sense with the UA concentration versus the contrast. What you can see here in this plot is that that there doesn't seem to be any logic on this. As you increase the percentage of UA in your free substitution, you seem to find less weight percentage of UA in your cells. This was quite interesting for us. You have to account for, of course, some things in your free sub cocktail. For example, when you put more UA in the sample, are you putting more methanol or ethanol, whatever your UA is initially dissolved in, and does that affect the way that your uranium is binding to your samples, thus affecting also the contrast? But it seems that increasing the UA percentage on the free sub doesn't seem to give you any advantage, at least in the amount of UA that you'll find in your sample in the end. So probably increasing your UA concentration when you're doing free sub will not give you anything extra in terms of contrast. So it's really difficult to appreciate what's going on. So the next step that we tried to do was, can it be that it will make sense if we actually compare the UA in the free sub versus the UA that it's been used in block stain on a chem-fixed sample? And here we try to keep the conditions a little bit more conserved. So we went for 0.1 UA free sub in acetone, so cryomobilized, cryofixed cells. And then we compare those with chemically fixed cells where we used still the osmium. We try to go for the typical TEM protocol with 2% uranyl acetate in block staining. Then we try to use our image analysis software Relate, where we were able to quantify the grayscale values of our EM images, but also quantify the weight percentage of our maps as a peak intensity. So what you can actually achieve is that when you try to create profiles of your pixels, you are able to compare between the contrast of the pixels with the weight percentage of different elements in the same pixel. So you can say, okay, if this pixel has a high contrast, does it have high osmium? Does it have high UA? This is the kind of analysis that we try to do here. Then we try to see if there was any correlation between contrast and the percentage, the weight percentage of the elements. So first, we found that on our free subsamples, when we have a high weight percentage of UA, we could find a higher contrast. So if you look at the first plot, you can kind of see that the curve for the uranium weight percentage is very similar to the curve for the electron image contrast. This makes sense. It's the only contrast agent that we put in this sample. when we do chemically fixed samples that were block stained, we actually start to appreciate some differences. Of course, there's osmium there that is correlated with the electron intensity. And you start to see interesting things. So there seems to be still a positive correlation with uranium, even though it's very little. So a much smaller value than what we see on the free subsamples. But we start to see also a positive correlation with chlorine. And we suspect this actually comes from the primary fixation, where you have all these ions in your fixative, and they actually contribute in a sense to give some more contrast to your sample when you're imaging, which is interesting. And how can you play actually also with the primary fix to enhance the staining of your sample? So in the end, we try to put all this data together. So comparing the chemical fixed cells with the free subcells, and we try to look at all the different element distribution. And the first thing you can see that is quite striking here is how much higher the weight percentage of uranium on the free subbed cells is versus the chemical fixed cells. So it seems like staining your samples just with a UA on the free sub gives you a much higher stain, and we still don't understand why this is happening, but there's some sort of interaction that doesn't allow the block stain of UA to bind as hard as what you can see on the free subsamples. This can be to do extraction, or it can be to do other things happening during the fixation protocol. I just want to also call your attention again here to the chlorine and magnesium. So depending on how you fix your sample, you might actually also affect the contrast that you're having on your sample. So moving away from uranium a little bit, we also thought this would be a very interesting staining to look at. So this is the zinc iodide osmium stain that's been used a lot in plants for studying the ER. And this is a type of protocol that also uses osmium. So osmium is very used still to volume EM and to TEM, SEM. So it's good to see what's going on when you have osmium interacting with different staining agents. So here we try to do the same approach of doing EDS and looking at how osmium and zinc were reacting with each other and reacting with the sample. And the first thing we can appreciate is that there are many different phases of staining in the cells that generate contrast in different ways. You can have places of your tissue where you have low osmium and low zinc. You have places where you have high zinc, low osmium, vice versa. So there's a lot of different combinations that allows you actually to separate your sample into different phases, which is kind of interesting because if you want to start masking your sample and having good solutions for automated segmentation, it might be something to think about when you're optimizing your sample prep. We had actually two different types of tissues where we could look at this specimen prep. So one was the venous flytrap leaf gland. And here we saw a very good correlation between contrast and osmium, between contrast and zinc. So this was very good. We were expecting this. When we go to maize root cells, different type of tissue, but still in plants, then we couldn't see any correlation with zinc and electron contrast. Even though lead and chlorine still have a highly significant correlation. So what's going on? It seems that more than ever, we should think about the type of tissue that we want to look at, the type of cells that we want to look at, and actually try to adjust our specimen prep to what we want to look at. So just to give you a quick summary, so EDS seems to be a good technique when you want to quantify the weight percentage of the elements that you put in your sample during specimen prep. And we can use our image analysis software to actually interrogate the correlation between weight percentage and your image contrast. UA seems to be a mystery. We really want to know more and keep exploring this to know what's going on, and why does lower concentration of UA in a free sub results in a higher concentration in your final prep in resin. So also, it was very interesting to me how different stains and protocols that you've seen published in a certain tissue that work this way can have unexpected results when you change cell types and when you vary only the type of cells or tissues and you keep everything the same. So more than ever, if we want to go into a type of more controlled way to preserve our specimens, lots of people want to do AI segmentation, which is more and more important to have consistent prep of your samples. You might want to use EDS when you are going through the optimization steps so that you have the most control over your specimen prep. Just because I showed you everything in 2D so far, because it's easier to do the analysis of the contrast, don't forget that you can still use EDS in your volume EM workflows, and this might also give you very interesting 3D segmentation of your elements, which will allow you to actually help with segmentation of your features in EM, and might even give you access to things you cannot easily see just by the EM contrast. So that's a wrap up. If you have any questions, please don't hesitate to get in touch. Thank you.
All right. Thank you, Pedro. Any questions for Pedro? All right. Any questions or comments from any of the previous talks? Thank you, Philip. Thank you, Lee. And thank you, Helmut. Phil, go ahead.
Sorry, Pedro, very interesting talk. I just have a question. Does your summary on your observations and of uranyl acetate, doesn't it correlate with what has been reported in the past on in-block staining with uranyl acetate for conventional TEM? That higher concentrations sort of don't really enhance contrast and instead can actually muddy up the cytoplasmic detail?
Absolutely. I just want to highlight that for the block stain, we kept the same concentration of UA always because we were aware. And we varied the concentration of UA on the free sub cocktails, just because there's a lot of different free sub concentrations of UA being used, especially if you start digging into correlative light to electron microscopy. You see people using a wide distribution of UA percentage that can be tenfold different from what some other people use, and then you still have good contrast and you still preserve your fluorescence, so you don't have so much quenching, but there's so much variability. Whereas on the block stain, we try to keep always the kind of standard, let's say something around 2% block stain for chemically fixed samples. Aqueous in this case, actually. I know some people do it in alcoholic solutions. This is actually something that could be interesting to look into as well, if there's a difference between aqueous and non-aqueous UA in ChemFix.